Okay, we start today with the last part, that is group 18. I hope to complete it today only, not much, because basically group 18 is inert gases. Group 18 is inert gases. Basically, their octet is complete. If their octet is complete, what happens? They are chemically inert, so very few chemical properties. Is clear? Now, what are the elements we have? We have helium. So we have helium, neon, argon, krypton, xenon, and radon. Of course, radon is radioactive. It's a radioactive gas. It's clear. Now all of them. So one very important point is all of them are gases. It's clear. And radon is radioactive. Now what happens is that we come to the electronic configuration. So what do we have? See, 9, 17, 35, 53, 85. Next will go and add 1 to that. So helium is 2. So 9, this will become 10. 17 will become 18. 9, 17, 35. So this is 36. 9, 17, 35, 53. So this will become 54. This will become 86. I told you, I remember only one, group. That is group 17. That is 9, 17, 35, 53, 85. So it becomes easy. Group 18, add 1 more, the problem is solved. So simply this has a configuration 1s2. This is a configuration of 1s2, 2s2, 2p6. So the outer electronic configuration is 2s2, 2p6. We have 1s2, 2s2, 2p6, 3s2, 3p6. Then we have 1s2, 2s2, 2p6, 3s2, 3s2, 3p6. Remember, 21 to 30, we have 3d10 filling up. This is 36. This is 36. So we'll have 3d10, 4s2, 4p6. Then 57 to 71 will be lanthanide. Okay. Therefore, F is getting filled. This is 54, so it will not get filled. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6. You have 4d10 but not 4f14, 5s2, 5p6. 5s2, 5p6. So here we'll have 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10. We have 4f14, 5s2, 5p6, 5d10, 6s2, 6p6. So the characteristic outer electronic configuration is characteristic outer electronic configuration is ns2np. It's a very simple question, but this can be asked in the entrance exam. The outermost shell is completely filled. It's clear. Now we come to what? Occurrence. There can be a factual question on this. When we talk of occurrence, what happens? Helium is 5.24 into 10 raised to minus 4. What do you call? Percent by volume. Percent volume by volume in atmosphere. So if atmosphere, if you take 1 liter, 5 into 10 or 100 ml, then 5 into 10 raised to minus 4 of that per 100, that much only will be, that much ml only will be helium. Is this point clear? So it's volume by volume of atmosphere. Then the second one, there's a question here. Which is the most, available or highest availability of, in which inert gas is highly available? No? So definitely not helium. Then we have argon. So argon will be 0.934, that is nearly 1%. It's 1% weight volume by volume of atmosphere. Then we have xenon. It will be 8.7 into 10 raised to minus 6. Then we have neon. Actually, it will be helium. Neon. Neon will be 1.82 into 10 raised to minus 3. Then we have krypton. It will be 1.14 into 10 raised to minus 3. Now about this, what you call radon. Radon is obtained. Now this is one thing you have to remember. What is the source of radon? Radon is obtained by radioactive decay. Radon is obtained by radioactive decay. Radioactive decay of radium and thorium. Is clear? So what is the source? You have radium. Okay, it is 22688. So when it gives out one alpha particle, helium 42. So this will decrease by 2. So decrease by 4, 224, and this will be 86. So that will be. See, Marie Curie, radon and polonium, she destroyed this. What she did was, in Poland there were old silver mines, So people had removed the silver and left all the other junk in the silver mine. She realized that there was radioactivity in that. Then from the silver mine, what happened? She found out that this gas was radioactive, radon first of all. Then she identified polonium. This is clear. So that's how she got Nobel Prize for the discovery of two elements. This is clear. The one more thing is radon has. So two questions. So this is basically only in JEE Advanced we have nuclear chemistry. Very rare you have come across nuclear chemistry in your what you call coursework. There was another place where we came across. That was, if you remember, discovery of neutrons. You had bombarded boron with what you call alpha particle, and you got a neutron. So discovery of neutron. Those were two radioactive reactions. And this one. So those three, that two and this one, please by heart it. Basically, there is something called as Soddy-Fajan-Russell's group displacement law. What does it state? That when a radioactive element emits a alpha particle, so this will be the parent element, this will be the daughter element. What happens? The mass number of the daughter element decreases by 4 and the atomic number decreases by 2. Why is it called as group displacement law? Because whichever group this was in, radon was in what? Radium was in radium. So this was in we have magnesium, calcium, strontium, barium, radium. Yeah. So this was in group 2. If it goes 2 places behind, 86, group 1, and then it comes to inert gases. So the logic of Soddy-Fajan-Russell's group displacement law is, when an element emits, radioactive element, not any element, radioactive naturally every element emits an alpha particle, it forms a daughter element. What is the daughter element configuration? Its mass number will decrease by 4 and atomic number will decrease by 2. That means the new element will be shifted 2 places behind the periodic table. From group 2, new element form will be in inert gases, group 1 and then inert gases. Clear? That's why it's called group displacement law. So I've given you a brief idea. One more rule is there which is not clear, but I'll tell you, if it emits a beta particle, atomic number increases by 1. So the new element shifts 1 place to the right in the periodic table. Then the daughter element formed has a very high energy level, so it emits gamma radiation. So gamma radiation is not going to cause any change in atomic number and mass number. So that's called as group displacement law. So you have 3 places where we are coming across this. Artificial transmutation was in your 11th slide I told you. Discovery of neutron, those 2 and this 2. Okay, this has been asked in MHCET. What they will do is, They'll just sow radioactive elements follow the first order reaction. So this disintegration of radioactive element is a first order reaction. So T half, in this case T half is 3.8 days. So this will be a connection of what you call inert gases as well as what you call chemical kinetics, because there the concept of T half is there. Why? Because radioactive decay follows the first order reaction. So please take down this much and we'll come to trends in physical property. So which is the most abundant inert gas that we have? The abundant inert gas will be most abundant. Most abundant will be argon, about 1%. There's a 1 minute this thing as far as internet was concerned. When you finish, you tell me. Okay. Not much. We'll finish this today only. So this was about. So now, what happens is, listen carefully. We are coming to physical state. Okay. When you are talking of physical state, periodicity in properties. Periodicity in property. When you talk of periodicity in properties, what happens? First is atomic physical state. The first one we are talking is physical state. All are, first of all, what we can say first or A. They are colorless, odorless, inert gas. Colorless, odorless, inert gas. The most important point over here is they are monoatomic. Now here comes the thing. How did they find out monoatomic? See, we have Cp. What is Cp? Mean molar heat capacity at constant pressure upon mean molar heat capacity at constant volume. For a gas, if it is around 1.66, it is clear. Then, so this is how they found out the atomicity of a gas, whether it's monoatomic or diatomic, thermodynamically. How did they find out thermodynamically? Cp is mean molar heat capacity at constant pressure upon Cv is mean molar heat capacity at constant volume. That was found to be 1.66. That's a correlation that it is monoatomic. It's clear. In your physics, they must have taught what is the value for diatomic gas. It's clear. Because you have that freedom, degree of freedom and all that. Huh? Then, so this value could be important for your MHT CAT local exam. Where there's too much emphasis on factual, what do you call. When we come to atomic radius, the second point is. The second one is atomic radius. What happens is, as we go down in the period, what happens? Atomic radii decreases. But because these fellows have got, what do you call, in the outermost shell completely filled, there is tremendous repulsion between the paired electrons. So they have a slightly higher atomic size as compared to the corresponding halogen, the adjacent halogen. So what happens? Since the outermost shell is completely filled, okay, what happens? There is tremendous repulsion between the electrons. Which electron? The non-bonding, lone pair electron. All are lone pair now. Any paired electron in the outermost shell is lone pair. So all the 8 are 3 or 4 lone pairs between the electrons. And this leads to a slight increase. This leads to a slight increase in atomic size. So therefore what happens? The inert gases, have what? Have atomic size slightly greater than is anomalous behavior. Technically, in a period, it should decrease, but slightly greater than the corresponding, slightly greater than the corresponding group 17 element. That is halogen. So this is a give scientific reason. So like GSR. How will they tune it in what do you call entrance exam? We have sodium greater than magnesium, greater than aluminium, greater than silicon, greater than phosphorus, greater than sodium, magnesium, aluminium, silicon, phosphorus, sulfur, greater than argon, greater than what do you call chlorine. So which will have the lowest atomic size? Always the halogen. Argon will be before that. So this is how they'll frame the question as far as what do you call entrance exam is concerned. Okay, same we have put it in. So this was about ionic radiation. Then we come to ionization enthalpy. Very interesting. So first and foremost point is they have the highest ionization enthalpy. They have, that is all of them. Helium, neon, argon, krypton, xenon, all have. So they have highest ionization enthalpy. But highest will come later. They have high ionization enthalpy. So what is more important from the entrance exam point of view? Helium has the highest ionization enthalpy. Ionization enthalpy in complete periodic table. In complete periodic table. Okay. How much is the value? 2372 kilojoule. Automatically you will ask me, sir, which is the one which is having least ionization enthalpy? Francium. I write that it is not connected to this topic, but highest and the lowest you have to, like we said, fluorine has the highest electron negativity, 4 in the periodic table. Is it clear? Then, so these kind of things are factual questions are important. So if helium has, so francium has least. But also remember one thing about francium, we know that mercury, then we have germanium, cesium, francium and gallium, I'm sorry. Mercury, cesium, francium, gallium are liquid metals. This may not be related to this chapter, but we will just, whatever we have to study, we'll study that. So these are liquid metals because you only are aware of what do you call mercury. But remember gallium, aluminium, boron, aluminium, gallium, indium, thallium. Gallium is used in high temperature thermometer. It melts at room temperature and boils at very high temperature. So that's why it is used in high temperature. So it's a liquid metal. So this, I mean, this is not in connect this, but better you know because these are all important data. Okay. Electron gain enthalpy, that much will complete and go, then you take down. Electron gain enthalpy. Obviously, they are very high electron gain enthalpy. They don't form compounds. One compound it is going to form that we'll see later on. It's clear. They have, because they have very high this thing. So all of them. So what can we say? All have positive electron gain enthalpy. Nothing of significance over here as far as electron gain enthalpy is concerned. So please take down this one. Then we will look at melting boiling point quickly. Liquefaction is very important. Okay. Priya, when you finish, you tell me because Shrestha has, I think, not been able to connect. So when you finish, you tell me.
Yes. We're done.
Finish. Chalo. Now, next one, what we have is not much in this chapter. I told you. After this, today is what? Today is Wednesday, na? And Friday, I am starting with polymers. So we talk of melting and boiling point. What happens? Helium has. So when we talk of melting point, element is we have helium, neon, argon, krypton, and xenon, and radon. Radon, we'll not talk much about it. Okay. So melting point in Kelvin. Okay, helium is 3. This is 24, and this is 84 Kelvin. This is 116, 161, and 212. We come to boiling point. 4, 27 Kelvin, 84, 87, sorry, 87. Then we have 121, 165, and 200. So radiation is melting and boiling point increases. But what happens? This is the question. 0 Kelvin is not achievable. Why 0 Kelvin is not achievable? Because if something comes to that temperature, what happens? It will become solid. Then the gas laws will not be applied. So that's why if you remember, we had drawn the graph, extrapolated it, and found that at minus 273, that is 0 Kelvin. Okay, what happens? The volume becomes 0.
cannot get such a temperature. The lowest temperature that we can come is helium. Yes, that is why you find helium is used in low temperature studies. If you want to come to absolute zero, very difficult. This is coming nearest. It is 3 Kelvin and 4 Kelvin. Boiling point is 4 Kelvin. That's why helium is used in low temperature study. You have this what is it, MMR and all that kind of this thing you do. Okay, there they use helium. The helium is placed between the magnets. That's why people find it very cold there when they go for that kind of diagnosis. Liquefaction, not easily liquefied because simple. Fourth, when we come to liquefaction, not easily liquefied because of the absence of van der Waals forces. Not easily liquefied. Okay. Getting helium liquid, that means you have to bring the temperature to this 4 Kelvin. Are you understanding? So you can imagine the amount of pressure that you have to apply and this thing, Joule Thomson effect, we can liquefy. But then amount of pressure that you have to apply. So not easily liquefied as it has less van der Waals force of attraction. Force of attraction. Okay, but liquefaction property will increase. Why will it increase? It will increase because of. Now, what is this liquefaction dependent on? Liquefaction is also dependent on enthalpy of vaporization. Liquefaction is dependent on enthalpy of vaporization. So what is it? Enthalpy of vaporization for helium is what? 0.0008 is all kilojoule per mole. Whereas neon, it is how much? 1.74. Then argon, how much do we have? 6.3. Krypton, 9.05. Xenon, 12.56. Radon, 17.2. Remember where we come across this? Ammonia. Ammonia had what? It had an enthalpy of vaporization, which was very low. So what was happening was, and it was endothermic. So what was it doing? In becoming it was taking heat from the water, and what was happening? It became a gas, and when it took from the water, the temperature of the water dropped down. This was how we made ice. So here you can see 1.74 kilojoule per mole. Even a candlelight will be much more energy than this. This is clear. So, and this is 0.008. So practically what happens? Because the enthalpy of vaporization is very, very low, what happens? You cannot liquefy this. This is clear. What is liquefaction? This you have studied in your 11th standard gaseous state chapter. We have something called as critical temperature and critical pressure. Yes, clear. In fact, I told you earlier on also, critical temperature I think is 29, because for carbon dioxide we needed the value. They are taught in 11th standard. I think I have the value here. If you remember, Andrews isothermal is what we had done in 11th standard. In Andrews isothermal, we had studied the liquefaction of carbon dioxide. It was, for carbon dioxide, it was 30.98 at a pressure of how much? The critical pressure was, I think, around 70. So 70 atmosphere pressure at 30.98, carbon dioxide started liquefying. It's clear. So if the enthalpy of vaporization is less, what is going to happen? The critical temperature will be high. Okay. So this is the connection that we are talking about. So this is not easily liquefied. See, when the critical temperature is high, okay, it is 13.98 because carbon dioxide has too much of, it is relatively lower compared to helium. At 13.98, carbon dioxide becomes liquid carbon dioxide is because it has higher van der Waals forces. So 13.98 we are considering as high temperature. So this will require much higher temperature and higher pressure. Is this point clear? So solubility in water. Next is solubility. So what can we say about this? They have very high critical temperature. Very high critical temperature. That is why it does not get easily liquefied. So we have solubility in water. Sparingly soluble in water. Now the question is, again this is connected to gaseous state in your 11th standard. There are different types of forces of attraction. Ion-ion attraction, ion-dipole attraction. Then we had what do you call dipole-dipole attraction. Then we had ion and a induced dipole. Dipole and an induced dipole attraction. So solubility in water of this is an example of dipole induced. So water is having a dipole. Water is a polar solvent. Dipole and induced dipole. Induced dipole attraction. So whatever little solubility that you are facing over, you are seeing that's fairly solid is because of dipole. Water has a dipole that induces dipole in the monoatomic molecule, and therefore there is little solubility. Very rare example, so it's very important. Please take down this much. Okay. Now we come to the chemical property. You know that it is not possible to vertical, but then there is one interesting reaction which was found out. Now, what is the basic concept behind it? See, what happened was there was this scientist by the name. So when you're talking of chemical properties, what happened? There was this fellow called Neil Bartlett, Neil IL. Bartlett. Now what he realized was oxygen and xenon, they had nearly a ionization enthalpy around value of how much? Around the value of 1170. So oxygen and xenon seem to be having nearly the same ionization enthalpy. And he succeeded in a reaction. What did he do? He took O2, okay, O2, and heated it with platinum hexafluoride, PtF6. And a reaction took place. O2 plus 1 electron went. I'm not talking about oxygen atom, oxygen molecule. From oxygen molecule, if you remove 1 electron, then this was around 1170 kilojoule per mole. This is kilojoule. So this experiment was successful. That is, he got O2 plus and PtF6. So he thought, why not with xenon, which has the same. So therefore, what happened was, what did he do? He reacted xenon with PtF6, and he got a compound Xe plus PtF6 minus. Xenon. First is the what? First write down the name of the cation. Then this is
iron instead of fluorine, PtF.
PT? Oh yeah. PtF. No. It is PtF6. Fe is not. It's PtF6. Okay. So now what happens? Thanks. Now xenon in the complex. How are we naming? Write down the name of cation. Then we have hexafluo. Then this was a negatively charged complex. So this was platinate. And then its oxidation number 5. So this compound was formed. So some more such fluorine compounds were found. Okay. I mean, this was the only thing that we know about what you call. Take down this. It's very, very important. This is the only successful compound that we found for what you call inert gases. Okay. Now see, after this, basically for each gas, they are given uses. Now just discussing this is for, it is more from the 12th standard point of view. So for each of this gas, two uses at least you remember. Is this clear? That is helium, basically used for low temperature study, cryogeny, neon, we know neon lamps, okay? Then these are used for basically welding, inert gas welding. So all this radon is used in what? Radiotherapy, cancer, photography of opaque steel castings. So these uses, you please check it up. This is more for 12th standard. But there is a question which they have asked, which concerns connecting this with nature of chemical bond. And I think some we have not done. So what is it that we have? This question has been asked in NEET. So we have molecule, what kind of hybridization it is, and then structure, and then we have number of lone pair. So this question has been asked in entrance exam, which I am consolidating. Some we have done in 11th standard. This we have not done. We have XeO3. It is sp3 hybridization. Structure is pyramidal. Moment you say it's pyramidal, what can you say? It has one lone pair of electrons. Then we have XeF4. This is sp3d2. So square planar. How many? It has two lone pairs. Then we have XeF2. It is sp3d. This is linear. It has three lone pairs. Then we have XeF6. Okay, this is sp3d3. Okay, disrupted octahedral. It has one, only four. Next one. Yes, one. So with this, I conclude this chapter. I told you it's very easy. I only wanted to have a look at the uses of each of this gas on your own. No big theory in that, but this is something you by heart. Many a times this question has been asked. So today is Wednesday. Friday, I'll be starting with polymers for you. Okay. That's exhaustive chapter. It'll take about 6 to 7 lectures. Slowly we'll do it.